So quantum mechanical theory describes the behavior of electrons in atoms. So we've been talking about how electrons behave like waves, and they behave like particles, and they occupy these strangely shaped areas called orbitals. So an electron configuration is what we call a description of the orbitals that are occupied by electrons in a given atom. So if we look at a hydrogen atom has one electron, right? So that electron is going to be in the lowest energy situation that it can be. So it's going to be the first principal energy level in an s orbital, and there's going to be one electron in there. So electron configurations take this form, 1s1. The superscript tells us how many electrons are in the orbitals. This is the type of orbital, and this is the principal energy level. Calculations with Schrodinger's equation show that that electron is going to occupy the lowest energy orbital, which makes sense. Everything tends towards lower energy. We can solve and do all kinds of cool stuff for hydrogen because it has one electron. But when you get more than one electrons, everything gets way more complicated. And so we can't actually solve Schrodinger's equation, but we can approximate it. And the reason that we can't solve this anymore is because now we have electron-electron interactions on top of all the other things. And so that makes it really, really complicated. So two of the things that affect multi-electron atoms are electron spin and energy splitting of sublevels. And we'll talk about those in a minute. Orbital diagrams are another way of showing what levels and what orbitals the electrons are in. So here, this is the orbital diagram for hydrogen. It's a box labeled 1s, and the electron is indicated with an arrow. This arrow only has half of its head. This one's pointing up. So the direction of this arrow tells us what the spin of the electron is. Pointing up is positive 1/2 spin, pointing down is negative 1/2 spin. If you look at a group of hydrogen atoms, they are not all going to have positive 1/2 spin. Some of them will be positive, some of them will be negative. Because what their spin is, it actually can change. It has to be one or the other, but they can flip. So just to make things consistent, when we draw these orbital diagrams, when we put the first electron in, we always assume that that's going to be the positive one. Okay? So that spin is a fundamental property. All electrons have spin. Yeah. Okay, so there's several principles regarding electron configurations. And we need to know the principles, but I don't require you to remember what their names are. I'm going to use their names, but I'm not going to ask you, what is the Pauli exclusion principle on a test? Because I have a hard time remembering which is which. What's important is that we remember the principle. Pauli exclusion principle. No two electrons in an atom can have the same 4 quantum numbers. Okay? It's like no two people in the United States can have the same Social Security number, right? It is supposed to be a unique identifier. So in a given atom, each electron has its own set of 4 quantum numbers. If 2 electrons are in the same orbital, like in the 1s orbital, 3 of their quantum numbers are going to be identical. N equals 1, L equals 0, M sub L equals 0. Those are all the same. The 4th number has to be different, and that's the spin. So if you have 2 electrons in there, they have to have opposite spins. One's plus and one's minus. And that way they have unique numbers, unique sets of numbers. So each orbital can have a maximum of 2 electrons, and they have to have opposite spins. This is true. Knowing the number of orbitals in a sublevels lets us figure out how many electrons could be in the sublevel. I don't think that's that important. I'm going to skip it. So let's look at helium. So helium has 2 electrons. So the electron configuration is 1s2. So now there are 2 electrons in that 1s orbital. When we draw the orbital diagram, that's that same orbital that hydrogen had, but now we have 2 electrons in it. One's an arrow pointing up, one's an arrow pointing down. Their spins are opposite. And so if we look at the quantum numbers for those 2 electrons, the first 3 are the same, but the last one is different. Okay? The sublevels in each principal energy level of hydrogen are all going to have the same energy because the orbital energy depends only on the principal quantum numbers. And so we use the word degenerate. Degenerate in chemistry means that these things have the same energy. But when we get to multi-electron atoms, because of interactions between them, notably shielding and penetration, the energy levels get split. So what we'll see in general is that within a principal energy level, the S is lower in energy, the P is next highest, D is next highest, and F is next highest. And that's nice because that's the order that they go, S, P, D, F. Coulomb's law is also an important concept in talking about electrons and charges in general. So this is Coulomb's law, the equation, and we're not going to actually calculate anything with it, but what we're interested in is the Q1, Q2, and the R. So Q1 and Q2 are the charges on the 2 different things, and R is how far apart they are. So if we have like charges, if they're both positive charges, or both negative, this energy is going to be positive, meaning that the particles will repel each other. If the charges are opposite, this one's minus and that one's plus, then the energy's negative and the charges attract. R is the distance between the particles. As R gets smaller, dividing by a smaller number, the energy gets bigger. So the closer the particles are, the larger the force of attraction or the energy of attraction. And the larger the magnitude of the charges, the larger the strength of interaction. So if you have highly charged particles, they're going to be more attracted to each other than things with lower charges. It's like strong magnets pull together better than weak magnets, right? And if you take a magnet and you stick a piece of, a note from your teacher or something on the, or maybe it's a wedding invitation, it's maybe more age appropriate. Stick the wedding invitation on the refrigerator, right? And it sticks up there just fine. Well, if you start putting more pieces of paper under that magnet, what's going to happen? At some point, this is going to slide down. It's like, oh, I can't handle it anymore. Why does that happen? Because each piece of paper increases the distance between the metal of the refrigerator and the magnet. And that's R. As R gets bigger, the attraction gets less. So it's the same with ions and protons and electrons. Any charged things is very similar to magnetism. Okay, so when we have multiple electrons, then we get attraction from the nucleus to the electrons, but then we also have repulsion between the electrons. So there's that nucleus, it's positive, and we've got these negative electrons. The negative electrons are like, get away from me, to the other electrons. I don't, right? Like charges repel, but they're like, oh, nucleus, right? They're attracted to that. So we've got these 2 competing effects here. So the repulsions will cause the electron to have a reduced attraction to the nucleus. We say it's shielded from the nucleus. It can't see all the wonderfulness of the nucleus anymore, so it's not as attracted to it. Part of its charge is shielded. So we talk about the effective nuclear charge, or ZF, F for effective. Z, again, that's the atomic number, the number of protons. That's the total amount of attraction that an electron feels for the nucleus. The closer an electron is to the nucleus, the more attraction it experiences. That's that distance thing again. The closer the electron is, the better it can see, this is how I think of it, better it can see the nucleus and the more attracted it is. If it's further away, it's not as attracted. So if the orbital or the energy cloud that this electron is in is able to be closer to the nucleus, it's going to be more strongly attracted. And if it's further away, it's less strongly attractive. And so what we'll see is that some of these orbitals will penetrate or go through other orbitals and get closer to the nucleus. Okay, pictures. So here we have a lithium atom, 3 protons in the nucleus. We've got 3 electrons out here. So these 2 electrons are in that 1s level, and so they are closer to the nucleus. This one is in the 2nd energy level, so it's a little further out. And if we think of this in terms of Bohr model, this is in the 2nd orbit, right? And these are in the 1st orbit. These guys are closer. This guy's further away. So what happens here is that as this guy looks towards the nucleus, he's a little repelled by these other guys hanging around. So not as attracted as if those weren't there. Okay, so this is a weird analogy. So you think about like a bodybuilder. Person is like amazing body, right? And they're on the beach, right? And they're wearing just this little tiny bathing suit, and you can see all of their physical glory, right? And so you're like, oh, wow, right? You're attracted, right? What if they're wearing a parka and snow pants and boots and a ski mask? You going to be as attracted? You can't see what's underneath, right? You're like, I don't know. Well, what if they're wearing shorts and a tank top? Then there's more traction, right? So I think of this as being a little bit like the nucleus putting on clothing. We can't see all of it anymore. It's sort of disguised, and it's not as attractive. Does that make any sense? Kind of? Okay. So the penetration then is, well, what if this electron is able to get closer to this and look under the parka? Unzip it, open it up. Oh, right? It's a really weird analogy, right? The weirder, the better. Okay? So it can penetrate through this repelling part and get closer to the nucleus. It's going to be more attracted. Okay? So how does that work? Well, we looked at these radial probability graphs. And so this is for the 1s orbital. We see that the electron is never at the nucleus, and as we move further away from the nucleus, the probability of it being there rises. In fact, it goes way off the top of the chart, even off the screen into the ceiling, right? And then it comes back down. That's for the 1s orbital. For the 2s orbital, most of it is out here, further from the nucleus, but the 2s orbital has a node right here, and it does have a little part that's way in close. It's actually inside that 1s orbital. And how can those orbitals be on top of each other? Because they are waves. They can be on top of each other. So that 2s the electron in there can get a lot closer to the nucleus than, say, in the 2p orbital. And so the 2s orbital, because it can get closer, is more attracted and is lower in energy than the 2p orbital. So if you understand that, that's awesome. If you don't, you're going to be just fine. Okay. So it's because of that penetration, those some orbitals being able to get in close or kind of get inside the other orbitals, that the sublevels of in a given principal energy are not the same. And in fact, the further you go, the more it affects things. And so when we get to the 4s orbital, it's actually lower in energy than the 3d orbital, even though it has a higher principal energy level. And those energy separations get closer and closer together. The relative energy ordering can vary among the elements, but we're going to learn the most common one, and we're not going to worry about the variations. So this is a diagram showing the ordering of the orbitals. So as we go up, energy is increasing. So each of these lines is representing an orbital. So in the 1s level, there's only one orbital, and this is the one with the lowest energy. It's closest to the nucleus, there's nothing in between, and so it's the most attracted. The next highest one is the 2s. For hydrogen, come on. For hydrogen, 2s and 2p are on the same level. They have the same energy. But hydrogen only has the one electron, so there's no shielding or penetration or anything like that. But because of those interactions, the 2s is lower in energy than the 2p. And then we go up to the third level, and here we have s being lower than p again. And then d is higher than p. So it's s, p, d on the third level. But this is where things get kind of crazy. The 4s is actually lower in energy than the 3d. So they start to overlap. And then we go, we have 4s, 4p, 4d. And again, the 5s comes in here, and it's lower in energy than the 4d. And that's all like, what the heck? I'm going to get to an analogy that hopefully will make it easier to think about. There's another principle. It's called the Aufbau principle. Electrons will occupy orbitals to minimize the energy. So they're going to fill up the lowest energy orbitals first. This is the filling order. You can memorize that if you want, but I'm also going to show you how it is all on the periodic table, and we can find it there once we learn how to look for it. Another principle or rule is Hund's rule. So when you're filling degenerate orbitals, like there's 3 2p orbitals, right? Each of them can hold 2 electrons. So when you're putting electrons in there, you're going to put each electron in its own orbital first before you pair them up. And then, the Pauli exclusion principle is that we can't have more than 2 electrons, and they have to have opposite spins. So first we'll fill them with parallel spins, and then we'll pair them up. Okay, so here's my analogy. The Quantum Hotel, a discount resort for electrons in Mrs. K's Chemistry Land. Chemistry Land is this fantasy place in my head. Very strange place, by the way. So all of this business with the orbitals and the levels and the sublevels is like, what the heck? It's so abstract. I tried to find something in real life that we could relate it to so that we could begin to remember it without rote memorization, because I'm not a big fan of just memorizing stuff. So here's my analogy. We've got this hotel, It's kind of weird. I'll draw a picture of it in a minute. The first floor has one room, and that one room is the S room. So since it's on the first floor, it's the 1S, right? The second floor has two rooms. There's an S room and a P room, 2S and 2P. The third floor has three rooms, S, P, and D. Guess how many the fourth floor has? 4. And the fifth floor would have 5. So the number of the floor tells me how many different rooms there are. The floor is the principal energy level. The rooms are the sublevels. Okay? In these rooms, we have beds, because, hotel rooms have beds, right? So the S room has 1 bed. The P room has 3 beds, kind of weird. The D room has 5, and the F room has 7 beds. What? Now, traveling with 6 children, that would have been so awesome, because there were many times we had to rent 2 motel rooms, right? Ugh, gets expensive. So another rule here is you can only have 2 people per bed, and they have to have opposite spins. What? What is a spin for a person? Okay, so this goes back to something I learned about at Fort Snelling, which is this really old fort in Minnesota. Cowboys and Indians kind of fort. So there's a bed, twin bed. So these guys, there were these soldiers, and they slept in the barracks, and the barracks had bunk beds, and they were just twin-sized beds. I think they were actually even a little more narrow, but because it's amazingly cold in Minnesota, like it was negative 40 degrees Fahrenheit. That's not the wind chill, that's the actual temperature. When it's that cold, flesh will freeze in 3 seconds. I mean, it's just, you can't even imagine how cold it is. It was minus 26 the last time I was there for Christmas. It got up to minus 12 that day. When it's that cold, and we actually did this, we took a pot of boiling water and we went outside and we threw the water in the air, not the pot, just the water, threw the water in the air, and it froze before it hit the ground, right? No lie, we did that. Anyway, so these soldiers back in like the 1800s, right, they didn't have down puffer vests and electric heaters and stuff, right? So how did they keep warm? They slept together, 2 guys in a bed. Like, ew, right? Modern people are like, oh, this is just wrong on so many levels. This was survival, okay? Well, how do you fit 2 people in a skinny bed? Well, the first person sleeps over here. You got to keep your limbs to yourself, right? And the other person slept upside down. So one person had their head at one end of the bed, the other person had their head at the other end of the bed. And this allows you to get closer and keep each other warm, okay? So this is what I'm talking about. This guy has spin up, and this is spin down, okay? So in this hotel, 2 people per bed, but they sleep like this, because even though it's a larger bed, they just, they think it's gross. So that's what they do. And I guess the other one that I didn't write on here, the floor is lava. Because I know when I was in high school and we would go on trips, and the guys, there's 2 double beds and there's 4 guys in the room. 1 guy slept on each bed and 2 guys slept on the floor, right? Or in the bathtub or something, because they weren't going to sleep in the same bed. You can't do that here because the floor is lava, okay? So you have to sleep 2 in a bed if necessary. Okay, so this is the correlation. The floor is like the principal shell or principal energy level. The rooms are the subshells, sublevels. The beds are the orbitals. The people are electrons, and the money, how much it costs to stay in the room, is the energy. Okay? Okay, so this is the hotel. Have you ever been to Vegas or driven through Vegas? There's some pretty weird architecture, right? There's one casino and hotel that's like this pyramid, right? And it's all like shiny gold and stuff. So this is the sort of thing you might see in Las Vegas, but this one's an upside down pyramid. You know, if you have any earthquakes, this would not work in California. But anyway, it is what it is. So this is the first floor of the hotel. There is one room there. It has one bed in it. 2 people can stay there. This is the second floor, green here, right? So there's 2 different rooms. There's the S room, and this is one room. This is the P room. They're on the same floor. Now, the third floor, there's an S room, a P room, and a D room. And, you know, I never put this in the analogy before, but maybe the hallway slants up. But what this is really telling us is how much does it cost to sleep in the room? The 1S room is the cheapest to stay in, and then 2S is next, and 2P, and 3S, and 3P. 4S is cheaper than 3D. Why? I don't know. How do they decide how much the hotel room should cost? I do have a reason for why the S room is cheaper than the P room. Because this red thing here, that's the elevator, and the ice machines and the soda machines. And so, you know, you're wanting to sleep at night. If you're in the S room, you're closer to that noisy crowd coming in way too late, right? So the further away from the elevator you are on a floor, the more expensive the room is because the quieter it is. Okay? So this is a certain cost. This is more, and this is the next one, and then that one's more expensive, and then this one, and that one, and that one, and it kind of gets confusing there, but again, it's all on the periodic table. Any questions? Yes.
So we're drawing the box, that's the orbital, right?
So
And
what I
then
drew here, what I was drawing here, I was drawing the sub-level. Each of these lines would be a bed, an orbital. When we draw the orbital diagrams, this is 1S, and that would be 2S, and this would be 2P.
Okay.
And so in the orbital diagrams, each box is a bed that could hold up to 2 electrons. Okay? Yes?
So each line would have an arrow pointing different directions?
Could have up to 2 arrows.
Okay.
Yep. So, unless a problem or the context tells you otherwise, we're going to assume that when we talk about an electron configuration, we're looking at every electron in the lowest possible energy state. So in the hotel, these electrons are cheapskates. That's why they're staying at this discount resort, right? So they're going to stay in the cheaper rooms. They're going to fill up all those lower rooms first. They're not going to go rent out the penthouse, okay? The number of electrons in a neutral atom is equal to its atomic number. So like cobalt is number 27, it has 27 electrons, okay? So if the cobalt bus came, there'd be 27 electrons staying in the hotel. Electrons with parallel spins in different orbitals have correlated motion that minimizes their mutual repulsion. Okay, so that's the fancy science explanation. Each orbital can hold a maximum of 2 electrons. And so, you know, these numbers here, so the S sublevel, the number of rooms go 1, 3, 5, 7, right? It's odd numbers. Each of these orbitals is like a bed. Each can hold 2 people, 2 electrons, so that would be 14 electrons possible in that F room. So the electron configuration is just a listing of those sublevels in the order of filling, lowest energy to highest energy. And then how many electrons are there is indicated by this superscript. And so you could think of this as maybe what the guy at the front desk is keeping track of, because when the next electron comes in, he has to know which rooms are full and where to send this guy, right? So this is his shorthand. He's like, okay, on the first floor, the S room, that one's full, it's got 2 people. Second floor, the S room has 2 people, that one's full. Second floor, P room, that one's full. This one's full, 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 right? And so then he's like, okay, well, the next one is, and he can send the next electron in there. So that's what an electron configuration is. It's the hotel clerk's shorthand. So we can make this even shorter than that. And this is sometimes called the inner electron configuration, or more commonly the noble gas configuration, because the beginnings of all of these are the same. So this is krypton, right? And if you add all those exponents up, it gives you 36, because krypton has 36 electrons. If we look at the next largest element with 37 electrons, it's all the same stuff, right? This is all the same as that. The only thing different is that there's an additional electron here on the 5th floor in the S room. So instead of writing all of this stuff over and over and over again, a shorthand notation is to use a noble gas. Use the noble gas symbol in brackets, and that represents all of this stuff, which is the same as this. So we're like, okay, it's the electron configuration of krypton plus this, okay? And you can only do it with the noble gases. Okay. So we did hydrogen and helium. So now let's go on and look at lithium. 3 electrons. So here's the first floor of the hotel. It has an S room. The second floor has an S room. All the floors have S rooms, right? And so with 3 electrons, the first electron's going to go in here. He's going to be spin up because that is sleeping the correct way in the bed, right? Most people, you don't go to the hotel room and you just put your feet on the pillow and your head at the other end. That's just not natural, right? So the first guy comes in and he does the normal thing and he sleeps right side up in the bed. The second guy comes in and he's got to share the bed with this other person. And so that's why he sleeps upside down, okay? He can't sleep on the floor because the floor is lava. Okay? Why doesn't he just get his own room? Because he's too cheap, okay? So the third electron has no choice but to pay more for a room. So he's going to get in there, and there's one bed in this room. He's going to sleep right side up in the bed. You with me? So beryllium has 4 electrons. So the first 3 electrons do the same thing that lithium did, and now the 4th electron comes in. He's too cheap to pay for a more expensive room. There's only the one bed in here, so he sucks it up and he sleeps upside down in the bed with the other guy. And the electron configuration is describing where these guys are. So 1s has 2 electrons, 2s has 2 electrons. So the electron configuration is 1s2, 2s2. Boron, we've got one more electron, 5, right? So the first guys do this thing, and the 5th electron has to spend more money for his own hotel room. So the next most expensive one is that second room on the 2nd floor, the P room. P room has 3 beds. So he's tired. He's just going to come in and flop down on the first bed, the one closest to the door. And he's going to sleep right side up. So then this is 1s2, 2s2, 2p1. Let's throw another electron in there, right? The next one comes in. He comes into this room, and there's one bed with this guy sleeping on it, and then there's 2 empty beds. What would you do? Curl up upside down with this guy you don't know? Or take your own bed? Duh, you're going to take your own bed, right? That's what the electron does. So he's going to take this empty bed and he's going to sleep right side up. Guess what the next electron's going to do? He's going to go in here, take his own bed. Now the next one that comes in, he's like, there's a person in each bed. I'm too cheap to pay for a more expensive room. I guess I have to climb in with one of these. I'll just take the one closest to the door. And so he'll be upside down in here. Does that make sense? A little easier to remember than all the other crazy things? So let's write an orbital diagram for argon and see how many unpaired electrons there are. So unpaired electrons are electrons that have their own beds. So the first thing to do is to figure out, well, how many electrons does argon have? 18. So argon has 18 electrons. We got argon, 18 electrons. I like the orbital diagrams, especially at the beginning, because they give us more of a visual, right, of what's going on. So I'm going to draw some hotel rooms here. So this is the 1S room. And then we've got the 2S room. And we've got the 2P room. And that second floor just has those two rooms. So now we're to the next floor. We're to the 3S, and then the 3P, and it turns out that's going to be enough to hold all these electrons. We're keeping the mixed up part for later. So now I'm going to put the electrons to bed. So the first guy goes in here, and the second guy is going to share. The next one goes in here. This next guy has to share. We get one in here. What's the next electron going to do? We're going to take his own box, his own bed, right? So he's going to go over here, and then the next one also gets his own bed. The next electron doesn't want to pay for that more expensive room, so he's going to go in here, and the next one's in here, and the next one's in here. And they're only paying for the more expensive room when they have to because they have no choice. So what do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You can remember how to do that, huh? You're just putting electrons to bed. Yeah.
So, if they're not in the same room, then they can't, like, have their own parking bed, right? Like, so, like, the S's, they can't go by themselves because they're not in the same place, right?
Yeah, so the S rooms, there's only one bed. If they were willing to spend more money, they could pay to spend the night in a more expensive room. But that would be for the electrons in a real atom. That would be an excited state, like you zapped them with electricity, and the electrons went up to a higher level, but they don't stay up there. They're going to come down. When they come down, they emit energy. So here we're looking at the ground state always. And so this is the one bed with two people. This room, this whole thing is one room, and these boxes represent the 3 beds in the room. Okay? Any other questions? Yeah.
So when you say ground state, you mean like it's neutral. That's why like lithium had 3 electrons, not 2.
So the ground state does not refer to whether it's neutral or an ion. The ground state just means that every electron is in the lowest possible energy level that it could be in. So all of these electrons are cheapskates, and they're only paying for the cheapest room available to them. An excited state, because this is a resort, right? There's a casino. An excited state was one of these guys went gambling and he hit a jackpot. It's like, oh, cool, right? And so he's going to pay to spend the night in a more expensive room. Which one? Depends on how much money he won. But he can't stay up there forever because that was like a one-time thing, right? So when he spends all that money on that one night, then he has to go back to his original room. So we have the excited state and we have the ground state. We will draw orbital diagrams for ions. And what we do there is we're looking at the number of electrons that the atom has, and then the charge tells us, if we have a -1 charge, we have 1 extra electron. If we have a +2 charge, that means we're short 2 electrons. And so we take that into account when we look at the number of electrons that we're putting to bed. Okay? Any other questions?